workshop. And yeah, I'll hand it over to Annika.
Awesome, thank you. Yeah, so I'll obviously have time for questions and discussion afterwards, but I also want to encourage, if there's any questions during while I'm going, feel free to raise your hand or just chime in. I'll try to answer some as we go as well. And I'll have a few questions for all of you. If you would do me the honors of participating, that'd be great. Awesome, so should I screen share? Cool. Awesome. So I'll be talking about bioastronautics today. And before we get to the content, just wanted to give a little bit of an about me, just to kind of say why you can maybe, I don't know, just why I'm qualified to be speaking about this, and just a little bit about the speaker. So I'm from New Jersey originally, and I'm Canadian, so I spent a lot of time hopping across the border. And I studied aerospace at MIT with a minor in creative writing, and I am now at CU Boulder doing my PhD. I'm in the home stretch of that, and I'm studying bioastronautics. In my free time, I volunteer with the Women of Aeronautics and Astronautics, which is a national organization with chapters at a bunch of different schools. And our purpose is basically to promote diversity and inclusion and programming for gender minorities in aerospace. In my other free time, I like to read, write, cycle, trail run. So that picture is me on Mount Evans here in Colorado after biking up because the road was closed to cars because of COVID. And so bikers got a chance to use the road, which was awesome. So jumping right in, what is bioastronautics? The short of it is that it's the study and support of life in space. And this middle definition here is the kind of official one, where we talk about making sure that we integrate the science and the physiological needs of astronauts with the engineering and the design solutions for human spaceflight. This is often confused with astrobiology, which sounds like kind of the same word rearranged, and that's study and search for alien life. And so while there's some overlap there about living in different environments, they are different fields. So bioastronautics is about how we live and work in space. So I'm going to quickly give you a brief history of spaceflight so you can maybe understand why we currently do things the way we do and kind of how we got to where we are today. So the beginning was in the 50s and 60s, and it's now known as the space race. It happened because of the Cold War, mostly. And there was a lot of trial and error. So the first animal in space was Laika. This is Laika the dog. She was launched on Sputnik 2 mission, Sputnik 1 being the first artificial satellite in space that launched in 1957, about a month earlier. And that terrified everyone because the Soviets had launched a satellite and it beeped. It just went into orbit and it went around and it beeped, and that's all it did. But people could hear the beeping if they tuned their radios correctly. And that terrified the Americans, right? And then a month later, the Soviets launched Laika. And she unfortunately died 6 hours into the mission, but they were clearly on their way to putting living beings into space. Just a short 4 years later, Yuri Gagarin became the first human in space. Here's Yuri. He launched on Vostok 1, which is another Russian mission, or Soviet mission, sorry. And he returned safely to Earth. And so the Soviets had shown that they could launch a human, support him in life or in space, and then bring him safely back to Earth. The Americans weren't that far behind. So again, about a month later, Alan Shepard became the first American in space. He did not reach orbit. He just went up and came back down, much like the commercial space missions we've seen recently with Blue Origin and Virgin Galactic. I'll be talking about those really briefly later. And a little bit later, John Glenn became the first American in orbit, and he stayed up for a few orbits. And they were both part of what was called the Mercury 7. And those were the first astronauts selected by NASA. And Mercury was the name of the program that was really aiming to give the Americans a proving ground for putting people in space. And I want to include this really old looking diagram just to kind of show just what our engineering was like at the time. Mercury was not a really great living space. It was basically the front seat of a car in space. And obviously beyond the capsule, there was, a vacuum. It was very dangerous. And it was controlled by a lot of former test pilots because they had experience with unproven flight vehicles in kind of extreme environments. And they knew, and a lot of the controls were designed basically to be similar to high performance aircraft at the time. Again, not a great place to spend more than a few days. Gemini was the next mission, or the next program that followed up Mercury. And in the background here, you can see the Mercury capsule next to the Gemini capsule, and Gemini is the twins constellation. And so it took 2 astronauts up at a time, and its focus was really to build towards Apollo. So we demonstrated keeping astronauts up for a week at a time, and demonstrating rendezvous and docking. So the ability to go up to another spacecraft and meet up with it, and to capture it in orbit. We also demonstrated EVA, which was the first extravehicular activity, the first spacewalk. So people were, Ed White was the first man to spacewalk, and he left the capsule and entered the vacuum of space. We also wanted to perfect reentry because Mercury had a few quirks on reentry, and it wasn't really a great ride for the astronauts, but unfortunately, no one was lost on reentry, but Gemini wanted to make sure that was perfect. Apollo, hopefully you all know about. It's the first time we landed on the moon. And it was really stirred and started by JFK, who during his speech in 1961 gave the goal of landing a man on the moon and returning him safely to Earth before the decade is out. And that put a timeline on it. And so Apollo did that. They had 11 flights, including 6 lunar landings from 1969 and 1972. And Apollo 11 is the famous one. That's the Eagle has landed. And that's the first time that Neil Armstrong and Buzz Aldrin went onto the surface of the moon. First and only time for them, but first time man was on the moon. And Michael Collins was the 3rd guy. He was up in orbit around the moon, basically waiting for the safe return of Neil and Buzz. And since then, 12 men have been on the moon. It's only been men so far. And we had our first space program related disaster, and that was a huge blow to the space program. Apollo 1, there was a fire in the capsule on the ground. If you've seen Apollo 13 or First Man, the movies, they show this in kind of the aftermath of that. And obviously Apollo 13, the movie, is based on the real Apollo 13, which was almost a disaster, but was one of the most incredible feats of engineering and improv that saved that mission. And so after Apollo, we had Skylab, which was really the first space station. So we really wanted to look at how we can live in space for a prolonged period of time. Skylab is kind of the forgotten one. It's not very big. It wasn't up for very long. It was only up for a few months, but it was much bigger volume. You can see the capsule, or I guess the whole station right here. And it had a crew of 3 for periods of a few months. So taking baby steps towards living in space. Space Shuttle was the next big one. Space Shuttle is what got me into space. And it was the first reusable launch vehicle. So it really changed the game. We could launch instead of, a couple times a year, we could launch every month. And we had a fleet of 6 shuttles: Columbia, Challenger, Discovery, Atlantis, and Endeavour. And we also had Enterprise, which was named after the Star Trek ship. And it was used for, it never went to space, but it looked like a glider. It still looked like a shuttle. And it was used to test out the approach and landing capabilities because hopefully, you know what the shuttle did, but it launched like a rocket and it landed like an airplane. And its first flight was in 1981. And it also brought with it a few accidents. Challenger was lost on launch, and Columbia was lost on reentry. However, it also did incredible work. It launched the Hubble Space Telescope, the Galileo mission, countless satellites, and it had a bunch of firsts. We were able to, expand the astronaut fleet from people who were basically just test pilots to people who were scientists, mission specialists, some civilians, and so space was starting to become more accessible. We no longer was it limited to this really small pool that was basically all white men who were test pilots. We were able to launch, people who were scientists like Mae Jemison, the first Indian American Kamanachala launched, as well as just like Onizuka, other people, really expanding space. And it also enabled us to build bigger space stations. So Mir was really the predecessor to the current International Space Station. It was launched in 1986 by the Soviet Union. At this point, the Cold War was kind of ramping down. And I say that because, at least in the space side of things, the Soviets and Americans were working together a lot. The crew on Mir was often a mix of Soviet cosmonauts and American astronauts. And And it was the first modular space station. So it was launched in pieces and assembled in orbit. It had an expected lifetime of at least 5 years, but it lasted about 15 years because it lasted from 1986 to 2001. And in this picture in the background is the space shuttle docked to Mir. And hopefully you all know about the International Space Station. It is our current space station, and it is a little bit bigger than Mir. It was launched in 1998, the first module, and so it overlapped a little bit. And 16 nations are collaborating and have built components for this space station. It's been continuously occupied since November of 2000, so that's kind of a fun fact, is that the last time all the humans were on Earth at the same time was in 2000, and they haven't been since. So that was my whirlwind of history, and that brings us to the kind of the current day. And hopefully, maybe you've paid attention to the news in the last few months. There's been a lot of talk about, the billionaire space race and commercial space, and what does this all mean? So a lot of the companies that exist right now fill different niches, and so SpaceX, for example, came out of the Commercial Crew program. Obviously, Elon Musk started the company, but they got a lot of their early funding from NASA. And Commercial Crew was a program started under Obama, which basically said, NASA can do things cheaper if we contract these commercial companies to do some of the work for us. And so they made these competitions where they would send out a bid, and companies like SpaceX or Northrop Grumman or Boeing would try to design something for the purposes that they required. And so that's how the Crew Dragon capsule came to be. And so that's been an incredibly successful program. Obviously, Crew Dragon launched people recently. It's been an incredible vehicle. The more, I guess, like controversial side of space, of commercial space, has been space tourism, with Virgin Galactic launching in July and Blue Origin launching a week and a half later. And yeah, people obviously give them a hard time because they're launching billionaires into space, and it's still very expensive to ride on one of these vehicles, and they're not really going into orbit. They're doing a suborbital flight. And there's merits to say that they also are making it still more accessible, because even though the tickets are still expensive, it's cheaper than, say, buying a seat on a Soyuz rocket and going to the International Space Station. In the third niche, there's also a bunch of other niches that come up in commercial space that need to be filled. So NanoRacks is a company that launches payloads off of the International Space Station. Then there's a kind of huge variety of small launch companies like Rocket Labs and ABL that are much smaller than maybe, say, the SpaceX rockets, but they launch smaller satellites for cheaper. And Rocket Labs is a cool one. Outside, they launch out of a bunch of different locations, but they're based in New Zealand, which is kind of cool. Also, you may have heard of satellite constellations coming up. I know Starlink has launched, at this point, thousands of satellites to provide internet and broadband to remote locations, which is really useful for search and rescue for people who live, in places like Alaska, where it's really hard to get a reliable internet connection. Other companies like Amazon's Kuiper and OneWeb have also been trying to do the same thing. And so that's kind of one of the new space races, is providing that service. Awesome. So we survived our history of spaceflight. We've gotten to the modern day. And now let's talk about how we actually do it, how we keep people alive in space. And I want to start with a person in space. Now, this person has just appeared in the vacuum of space. What do we do to save them? What is the first thing that will kill you in space? Feel free to drop it in chat or just call it out. Awesome, we got lack of oxygen, the vacuum, difference in pressure. Big list, lack of oxygen, pressure, the temperature. Yeah, in a lot of movies, you see people, lack of O2. Yeah, in a lot of movies, you see people go really cold. So a lot of people think it's the temperature, but difference in pressure in the vacuum, that's the first thing that actually kills you. So the vacuum is the thing that causes the water to boil out of your eyeballs, out of your tongue, oh, space junk. That's a really good guess as well. Luckily, space is really big. So even though there is a lot of junk up there, the chances of getting hit, like the movie Gravity, are actually really, really low, though that's still a growing problem. But in terms of just existing in space, the vacuum is the first thing that will kill you. So cool. we got the vacuum sorted. Let's put an atmosphere around the person. So now they're in a little bubble and they have an atmosphere. Let's just give them like whatever we have, at sea level, mostly nitrogen, some oxygen, some trace gases. They're doing fine. They're in this little bubble with an atmosphere. Okay, what kills you next? You would be technically dead. Say the vacuum didn't kill you. We got an atmosphere in time. Lack of O2, lack of water. Interesting. No food. Yeah, we're getting there. Loneliness, change in temperature. Let's say we've taken care of the temperature also with the atmosphere. Radiation. These are all really good guesses. These are all space hazards. Yeah, so the first thing isn't actually the lack of oxygen or using up all the oxygen, it's the buildup of carbon dioxide. So as you breathe in, you're breathing in oxygen and you breathe out carbon dioxide. In space, there's not the same gravity situation and we don't have anything filtering out that CO2. So here on Earth, we have gravity that pulls the air down and mixes it around. So the CO2 just kind of like disperses into the building. It disperses into the atmosphere. The wind comes by and you get new oxygen. You never think about the CO2 building up around you. But in space, if you have nothing filtering out that carbon dioxide, that CO2 is actually going to build up around your head and it's not going to be pulled out of the atmosphere. And so eventually you will die from that before you run out of oxygen. So the oxygen's still there, it's floating around, but that little bubble of carbon dioxide is what's going to get you. So we need fans and we need some way to remove the carbon dioxide. We need to mix the atmosphere. We need to pull out that carbon dioxide. And once we've done that, yes, we need to pump oxygen back in. So the lack of oxygen is the third thing. And then finally, there's one more thing in the atmosphere that will kill you if you don't take care of it. Does anyone want to do one final guess on what that is? Just in the atmosphere, not talking about food or water yet. It's a really tough one. I didn't get this when my professor asked me the first time. So the humidity will actually, you can drown in the air. If you don't remove the water that we are breathing out, it will eventually accumulate in the air and a person will suffocate from the water in the air, which is the kind of crazy one. And so I don't know if you've ever been out on kind of a cool day or you've gone up against the glass and you breathe out and you see all of the humidity from your breath condensating against the glass, or being like all smoky when you breathe out. That's just you have a lot of water content in your breath, and so eventually that gets pumped back into the air and eventually it'll saturate. So we need to pull that water out of the air. And once we have systems that pull out the water, we have systems that pull out the CO2, we have some fans to mix it all around, and we got something pumping oxygen back in, then this person is happy and alive. So yeah, space is tough. We went through that exercise just to show you kind of the complexity of something like breathing and existing before we even get to food and water. Because in space, even that's something that we can't take for granted. So in space, everything, it's helpful to think that everything is trying to kill you because it kind of seems like that sometimes. In space, there's not any medium, there's no air, so sound doesn't travel. Literally, no one can hear you scream. And just to kind of give an overview of different environments, obviously the vacuum in orbit is dangerous. And on the moon, we have some other issues. We have some gravity. We have about 1/6 the gravity of Earth, but it's really dusty. And lunar dust is actually really dangerous for your lungs if it is breathed in. And so we had to be really careful doing spacewalks, not to track that dust back into the lunar lander and breathe that dust back in, because it will cause little tiny cuts in your lungs. And there's also no atmosphere on the moon, so all of the vacuum issues apply on the moon as well. On Mars, it's about 1/3 of the gravity, and there is an atmosphere, which is great. It's not really that helpful to us because it's mostly carbon dioxide, and we have these big thermal extremes on Mars. The day to night shift is like over 100 degrees, and so again, you need a spacesuit, you need a lot of insulation. Someone mentioned the radiation as well. The radiation around Earth isn't too bad. Just because Earth kind of shields the astronauts that are in the space station right now. However, when you travel to somewhere like Mars, you're in between planets for a long time, and that radiation is a little bit worse. And same on the surface of Mars. The radiation out there is worse than it is at our own planet, because Mars doesn't have quite the same atmosphere, and it doesn't have a nice, strong magnetic field the same way Earth does. And radiation won't kill you immediately, but it will cause issues down the road. It can potentially cause cancer and radiation diseases like that. So in space environment, we tend to break these things into hazards and risks. And this, I won't quiz you on this, but a hazard is a situation that poses threat to life. So like a knife hanging from the ceiling is a hazard, but it's only a risk if it falls. That's the way I think about it. That's kind of a trite example, but in the space environment, we have a bunch of hazards. Like I said before, we have microgravity because your body changes to microgravity, and we'll go over that a little bit. And we have those thermal extremes. We have the vacuum, we have radiation, and we have the space debris. We have micrometeoroids and little chunks of things flying around really fast. And we try to mitigate these through different means. We design countermeasures for microgravity. We make the astronauts exercise a bunch. We insulate and we radiate heat out to address the thermal extremes. Obviously, we make a structure and we make it pressurized to combat the vacuum. And we have mostly shielding for radiation. And you can do active or passive shielding for that. Passive shielding would be something like a lead-lined spacecraft. And then active would be something like an electromagnetic field that is put around the spacecraft to shield it, much like our own magnetic field around the Earth. And then micrometeoroids, again, shielding. So on the International Space Station, we have 2 layers of the space station. And the job of the first layer is basically to fragment whatever hits it so that it is in a million pieces and it won't go through the second layer. And here's a hole that's about 1 millimeter in diameter on the International Space Station because it does get hit sometimes. And so it's good to keep track of that. So in the bioastronautics world, we have some sayings that we like to go through when we're thinking about how to design a spacecraft for people. We want to keep them alive, healthy, happy, and productive in that order. And this is kind of like a fake equation we use to think about that. So we have the sum of the spacecraft mass, so the total spacecraft weight, should be a function of the physics, physiology, the safety, and operability. And what do those words mean? So the physics are things like getting there. We need to get the rocket off the ground. We need to put it in orbit. We need to obey the laws of motion. We unfortunately cannot go back in time and tell Newton to uninvent gravity, because clearly gravity didn't exist before Newton. I'm just being sarcastic, but yeah, we have to obey the laws of physics. The physiology is the human body. There are certain things that we just need. We need air, we need water, we need food. And depending on how long we're up there, we need a certain amount. And so these are non-negotiable. We need to address the physics and physiology. Your trade space, the things that you can kind of like play with a little bit, are the safety and operability. And obviously we want it to be safe, but how safe is the question. So on the space shuttle, we had 5 flight computers. That's a lot of computers. And that was to make sure that they worked properly, and they all voted. And so when something was going wrong, or one computer had something different, we would check the other 4 to make sure that those were in line. Again, 5 computers is expensive though. It takes up space, it takes up design, it takes up physical mass to launch. And so that's a question of whether or not you need that. Operability is a kind of a fuzzy word that includes how easy is it to operate. When you're sitting in a plywood chair, like that gets the job done. But if you're sitting in a nice like gaming chair that's nice and cushy, or like a lazy boy, well, it's a little bit more comfortable. And it's kind of nice to have one of those in your living room, more so than maybe like a stool or a camping chair. And so operability comes into all the nice stuff, all the things that make astronauts happy and productive. And I should just say, like in spaceflight, we often speak in mass, and that's because mass is the most direct kind of corollary to money, because it takes a lot of money to launch things. And so we always want to make sure things are minimized in mass. All right, next questions. This is something people don't really think about that often, but how much water by mass do you consume a day? Does anyone have any guess? Say in pounds, kilograms, cups. 2 kilograms? Yep. Yeah, that's actually really close. Do you want to take a guess on how much food you consume a day in weight? 5 liters. 5 liters is kind of little. You could get by with that. That's not a great amount. 10 kilograms of food. Wow, that's like 25 pounds. That's a lot of food. Maybe 3 kilograms, five. Awesome. Okay, how much oxygen by mass do you consume a day? This one's hard because we don't really think about oxygen as really taking up too much weight. 1 ton. Wow, it's like an aircraft engine. 5 kilograms. That's a good guess. A lot. Yep, a lot is 20 kilograms. Wow. Okay, 10 kilograms. Awesome. So we're going to go back to our little buddy in space. 10,000 liters. Okay. Here's everything you need to survive in a day. Apologies if these are in kilograms, because we speak a lot in metric, but oxygen is a little bit under a kilogram, so not that much. It's about just under 2 pounds of oxygen. And this unit of measurement here is kilogram per crew member day. So it's assuming that we have a 70 kilogram male crew member, just for kind of the upper bound of person. Obviously, smaller people, or often women, tend to be on average smaller and take up less resources. Water ends up being close to 4 kilograms. So I think we had some pretty close guesses to that. We had 2 kilograms as a guess as well. But ideally you have more potable water, drinking water. And then food actually is too much. Food is really only like a little bit over a pound of food per day. And this is all dehydrated food oftentimes. So that's actually a little bit less weight as well, because we do get some water from the food we eat. Like an apple has quite a bit of water in it. However, that's not everything we need to survive in a day. There's a lot of stuff that kind of comes by us that we don't think about, like hygiene water. When we're washing ourselves, there's anywhere from half a kilogram to 25 kilograms, depending on if we're showering or if we're using the toilet or if we're brushing our teeth. So that's quite a bit of water. In space, you don't shower as much, and we can talk about that as well. Nitrogen, that's a passive gas that we breathe in. And we breathe out again, and it goes into our bloodstream, but it kind of just sits there. It doesn't actually do anything. It's inert. Here's all of the outputs, and these all kind of surprised me when I first learned about them, because I don't think we really think about what we leave in the toilet, or like what we actually exhale. Like I said, we exhale a lot of water, up to sweating and exhaling. It's not like 5 pounds of water, 2.2 kilograms. That's kind of a lot of water, at least I thought, to be losing a day, which is also why you need to drink a lot of water. Obviously, with your urine, there's both the liquid urine and urine solids that are dissolved there. And so we need to make systems that process both of that, because we got to reclaim that water somehow, and we need to make sure we get everything out of it. Same with sweat solids. If you're sweating, some of the sweat isn't just water. You take a lot of salts out of your body that way, which is why when you're really thirsty, actually things like Gatorade or similar sports drinks will have a lot of dissolved salts in them for you. Again, same with feces, solids and water. We got to find a way to separate that out. We got to make sure that we're doing something safe with all of that waste. All right, we've survived the grossest part of this lecture. I know you guys are doing a design challenge, and so I also wanted to, I can give you the slides afterwards, but we use a big reference sheet for all of this design. It's called the Life Support Baseline Values and Assumptions document, the BVAD. This is the reference number, and there's a link to it that I can provide, but it's like the source document for sizing all of the environmental control and life support systems. And so that makes sure that all the designs are on the same page. They're often overestimated to make sure that we are planning for the worst case scenario for a large person, because every human body is different. Okay, so we have this person in space. They're alive, they're in a pressure vessel. We've talked about kind of like what the human body needs in a day. What else do we design for in space? Well, in the internal environment, we have a bit of wiggle room when we're defining the atmosphere. Do we want to keep it at sea level? I'm not at sea level right now. I'm actually at about a mile high. And that means the pressure around me is quite a bit lower than at sea level, and I have less oxygen. And I'm doing fine. So could we just do that? Could we put all the astronauts at altitude? Could we put them at 8,000 feet? That's what most aircraft are kept at. What temperature do we put it at? Well, we want to try to keep it in a short sleeve environment, that's what we call it, so people can wear short sleeves if they want to, and be comfortable and not too warm. We also want to make sure we're designing for contaminants. Like I said, you lose a lot of stuff off your body throughout the day, whether it be like skin cells, hair that just kind of comes off, stuff like that, like sweat solids. Maybe someone sneezes. We want to make sure we capture all those contaminants and we get rid of them, because that's kind of gross to be floating around the cabin. We also designed for degradation of the cabin environment. So what is it? So what does that mean? I spoke about the micrometeoroids and space debris, and sometimes those little tiny bits hit the space station, and maybe a big thing hits the space station, not like catastrophically big, but enough to cause a leak, like a small hole. And this happens. This isn't super common. Like I said, space is really big, and the space station can maneuver out of the way of things, because we do track space debris down to the size of about a quarter, which is quite small. But sometimes a quarter-sized thing is enough to cause a hole. And so in that case, we designed the space station such that we can feed the leak, right? And that means that we should be able to have enough air that can be pumped into the space station to then have that little leak. And that's okay. The astronauts will be fine. It should be able to do that kind of indefinitely until they can find the leak and fix it. So again, that's what we designed for. That's kind of the baseline. That way, if we're designing for something below that, we don't have an emergency when there is a leak. Other factors, like I mentioned before, radiation protection, acceleration, vibration and noise, and illumination. The space station's pretty loud. In most human spacecraft, they're all pretty loud. You're living kind of alongside the systems that are keeping you alive, and they vibrate and they beep and the lights hum. You're kind of living in a lab. And so we need to make sure that the astronauts have a place they could go where it's not as loud. And the light is still something that we're designing. These lights aren't really great for living. I mean, you're living in basically these big LED lab spaces. And so trying to find lights that are a little bit softer that can mimic daylight is important for mental health. I also just wanted to include this picture of Katie Coleman because she's a cool astronaut, and she played the flute. So she would bring the flute up and have concerts from space, because recreation is also important. And we can talk about that later too. So like I mentioned before, the internal environment is super important. And so this is the crew quarters in the International Space Station. On the space shuttle, we didn't have this. We had basically sleeping bags tied to the walls of the cockpit. And that's not very personal, but you can handle that for like a week, right? Like you can go camping and handle living in a tent for a short amount of time. But anything longer than like a week or two, and that starts to get pretty uncomfortable. And so when you're staying in space for months at a time, you really want your own personal space. And so here you can see their sleeping quarters, again, tied to the wall, because if you're not, you'll float away. You have your own little workstation where you can talk to friends and answer emails. And then you have your wall with Velcro where you can put all your stuff Velcroed onto the wall so it doesn't float away. And you can notice all this padding. That's to help keep the noise down. So yeah, noise and vibration, big ones. Lighting, like I mentioned, ISS doesn't have daylight in a conventional sense, but it does have a sunrise every 90 minutes every time it goes around the Earth. So there's very few windows, but if you are by that window, it's kind of like changing light constantly. And so we need to make sure that we have light that can help people sleep at the right times and just feel more comfortable. Light can also be used to show direction. So it's really hard to actually know where you're going on the space station because every direction is viable. You don't exist in a vertical space anymore. If you're standing in a room right now or sitting in a room, try to imagine if you weren't, I guess, like committed to the ground. Imagine being able to float around and changing your orientation in a room. And suddenly, it's a lot easier to get a little bit disoriented, especially in the space station where everything kind of looks very similar. So what is ECLSS? ECLSS, I mentioned before, and it's really important, and that's the environmental control and life support systems. And it's all the stuff keeping you alive. So again, it regulates the atmosphere, manages all the water, provides food, and collects waste. And the type depends on, the main factors are duration of mission, destination, crew, and ability to resupply. And this ends up being a huge chunk of mass of the spacecraft, because here's the International Space Station ecosystems here on, that's when they were on Earth. And they're massive. They're these huge cabinets that are built into the walls. So it's really important to know how to upkeep those and how to keep them going in space. You don't need to look at all of the bits of this diagram, but I just wanted to include it to show how complex that system has to be for the astronauts to stay alive. Again, like all those things that we had to address are in a loop, and we're trying to reuse as much as possible to save mass. And so we end up with a lot of stuff going around and around and getting condensated back into potable water, in the case of the stuff that we're breathing out and sweating out, and the stuff that we're trying to filter out of waste and urine. Again, some waste is just not reclaimable, and that gets put onto a garbage disposal capsule and burnt up in the atmosphere. So what happens to your body in space? I mentioned that you have to design to mitigate the effects of microgravity, but what are those effects? So the short-term effects of microgravity are that you grow immediately 1 to 2 inches, which just sounds great. You get a little bit taller. Your abdominal girth decreases, and that's because all of the water in your body is basically relocating, because it's used to you being on Earth. It's used to having a kind of its own pressure gradient just from the weight of your body on itself. And so your internal organs also shift around because they don't really have to be in that order anymore. And we're not talking anything like drastic, like your stomach doesn't end up in like your foot, but it does kind of like shift up a little bit. Everything kind of like stops just resting on top of each other. Your default posture is altered. So if you ever see a workstation in space, it's not like a desk where you're sitting like you would on Earth. It is actually kind of built to be in the fetal position, because your body naturally curves kind of like a baby would be in the womb. And that's just kind of a natural way that we float. And so when we're floating like underwater, that's how we float there as well. So a lot of the workstations are built to be accessible like that. I mentioned the fluid shift, and then the vestibular system is impaired for like for a day or two, and that's your inner ear. So people will often spend the first day throwing up, being kind of dizzy, having vertigo, and that's because your inner ear depends a lot on gravity. And when there's no, obviously we're in microgravity, when there's no direct down direction, your body gets a little bit confused. The long-term ones are the ones that we really have to watch out for though. So your blood volume loses volume, and then your muscles start to atrophy. And so we try to combat that by having a lot of exercise equipment. And so we're, you know, in this case, it's a treadmill, and we have to bungee people down to try to simulate gravity. That helps keep the bone density also up. It's still, astronauts still lose bone density, but not as much. Cardiovascular deconditioning happens as well, just because you're not using your heart as much, because it doesn't have to work as hard against gravity. And so these are all things that we combat with like 2 to 3 hours of exercise a day. And that's because we want to keep the astronauts obviously able to return to Earth and walk once they get there. For a mission to somewhere like Mars, this is a huge concern, because the astronauts need to be able to stand up when they get to Mars, to move stuff around and set up their camp. And more than likely, if they're in space for 6 months, they're not going to be able to stand up right away. If you've ever seen astronauts return to Earth, they will be fine in a day or two, but they'll have to regain some of their strength. In that first day, they basically just have to get carried everywhere because they're not used to gravity. And the final weird long-term effect is vision defects. So astronauts actually lose a lot of their vision in space, and that's kind of up in the air right now as to why that happens, but it's thought to be from your eye deforming from lack of gravity. And it's nothing drastic again, but it might be that you just have to, now you have to wear like a little bit of glasses, or your vision gets like a little bit worse. We talked a little bit about EVA and about going outside of the spacecraft, but we didn't talk about spacesuits. So the suited environment, there's not one size fits all. There's a bunch of different types of spacesuits. So we have Mae Jemison down here in the launch and entry suit, which is our launch, entry, and abort suit. And that's just a pressure suit, kind of like a pilot would wear for a high performance aircraft. And that's just in case the vehicle decompresses. That won't save them in space, but it will keep them safe in high altitudes. The lunar surface and the orbital EVA suits are quite similar. They're basically spacecraft for the people to be in. It has to be pressurized, it has to provide and filter out all of the atmosphere. You also kind of feel like a hamster because you have a little bit of a water spigot that astronauts can use to get water, because the spacewalks take quite a while. They take up to 8 to 10 hours working. Some people will also mount a protein bar inside their helmet that they can chew on. So again, it's just a long time. You also have to protect from those micrometeoroids and orbital debris, as well as dust, to make sure that they're staying warm enough. Obviously on the surface, mobility is a little bit more of a concern because you actually have to support weight and walk around. Near Earth objects, NEOs, that's like asteroids. There was a program in the 2000s to return to an asteroid, or go to an asteroid with people and then return back to Earth. And the suit designs for that concept that never actually happened had to be somewhere between the orbital and the surface ops EVA suit. I also wanted to include the Russian suits here. That's the Soyuz suits. They're similar to the shuttle suits, just a different color. Suit design considerations. So we want ventilation. We want to make sure that they're not getting too hot. And like I said before, mobility and dexterity are really hard to do and also really important. So we actually can't keep the suit at 1 atmosphere of pressure because you wouldn't actually be able to move. You'd be kind of like the Michelin Man. And you wouldn't be able to move any of the joints or use any of your fingers. And that's really important when you're working with tools outside the spacecraft. So that's one problem. We also, it's difficult to design all of those joints to fit everyone. And unfortunately, one size really does fit no one. And astronauts will often have to deal with chafing, and they'll have to deal with occasional shoulder injuries because it's really hard to get that full range of motion in a suit that's pressurized. Decompression sickness is a concern. Like I said, we can't inflate the suit to 1 atmosphere. So when you leave the space station and go into a suit that is at a lower pressure, it's kind of like you're rapidly ascending from a scuba dive. And so how do we prevent them from getting the bends or decompression sickness? For those of you who don't know what decompression sickness is, it basically occurs when that nitrogen that's usually just inert in your bloodstream, it bubbles back into the blood. Usually it's dissolved in your tissue. But when the pressure gets lower, it hasn't had time to adjust, and it actually will leak back out into the blood and cause problems by being a bubble of nitrogen in your blood. This can be avoided through either keeping your cabin pressure lower and slowly lowering the cabin pressure on board the space station, which they did on shuttle. They would actually raise the altitude of the cabin to 10,000 feet overnight. And then they'd have people pre-breathe. And pre-breathing is when you breathe a basically like pure oxygen to flush out that nitrogen from your body so that you don't get the bends. However, the problem from breathing pure oxygen is also if you breathe it for too long, you get oxygen poisoning. So that's a huge concern for high performance scuba diving and for EVAs. If you were to breathe pure oxygen for over 12 hours, that would be a problem. Also, I know I want to try to get to the questions, so I'm going to speed through the next bit. But I just want to include this picture of David St. Jacques. He's a Canadian astronaut doing a neutral buoyancy lab dive. And that's when the astronauts practice their spacewalks in Houston and Texas. And they'll have mock-ups of different spacecraft of the space station, and they'll practice everything 1 million times. And they have a team of support divers down there. And this is a good chance to try to just run through everything. They're in the real suits. Obviously, they're not in space, but water is a pretty good analog. Psychological needs. They're just as important as physical needs, but it's harder to measure them. Things like comfort are hard to solve in space. Obviously, you're living in basically a lab. So we really try to make sure astronauts are comfortable, have their personal effects. Space is inconvenient. You're living with like 6 other people. There's probably no showers. You have a limited amount of clothing that you brought with you. The meals kind of suck. There's like dehydrated food. So people often will sometimes lose weight in space just from not eating. And there's only so much you can do in space. You are in space, which is cool, but you can't go for a run anymore, except on the treadmill. You can't necessarily go to the movies. We've now been able to obviously upload movies for the astronauts now that we have the technology to stream that. And so that's been a huge improvement of quality of life for them. You're also living in a really dangerous environment, and that's really stressful. Obviously, I don't need to remind people that there was a pandemic. There is a pandemic still going on. And there's a lot of parallels to being isolated for long periods of time and to living with just kind of a chronically stressful environment. And a lot of schools and different NASA centers have done studies by interviewing people, just everyday people, about their COVID experience to try to understand the effects of isolation, of stress, of that kind of long duration psychological problems and stressors. And that's just super helpful in generalizing that to astronauts, because we have so few astronauts that we can't get a big sample size. We've only had about 100 and something astronauts. So being able to seize that chance and talk to the general public about similar things is really valuable. Crew accommodations. This basically encompasses all of that, making things nicer for the astronauts. So it's all the stuff that serves human needs that aren't keeping them alive. So things like equipment for cooking. Did you remember to take a toothbrush with you? Do you have seats for the astronauts? Do you have enough mass margin to include seats? Like I said on Space Shuttle, they didn't have enough room to have their own quarters. So they were literally tied to the walls in these kind of sleeping bags. And on later missions, they installed these bunks. And that was a huge improvement because you could sleep in kind of your own private little box, which is better than being tied to the walls of the cockpit. Again, there's another NASA handbook that you can look up. All of NASA's reference stuff is available online. You just gotta kind of search for it because they are a government agency that is public. Other design considerations include the food preparation. Do you need to heat it up? Is it just fresh out of the bag? How long does it last? Do you need a refrigerator? Stuff like that all needs to go into the design of your spacecraft. Sleep accommodations, like I mentioned, are driven by duration. So for the lunar lander, they were on the moon for 3 days. They didn't have this because they had gravity on the moon, however small that was. They didn't have this. They had 2 hammocks strung up over each other. So Neil and Buzz slept in basically a closet in a hammock for 3 days. But again, you can do anything for 3 days, right? When you're up there for months, you want to try to have a nicer place to sleep. And the final question is, who's going? So you're going to design things differently for career astronauts who are used to being test pilots or used to being scientists or engineers who maybe understand systems better or are kind of signed up for it and signed up for that tough part. But if you're sending tourists up, they paid a lot of money for the future to go to space, to have this like luxury experience. And so you'll design those things a little bit differently because of your clientele and kind of who you're designing your spacecraft for. Just want to include some pictures of the inside of the space station. Again, like food is hard. Whenever they can get fresh vegetables, fresh fruit, it's a big day on the space station. This guy looks so excited to see some lemons. Like I've never been that excited for lemons in my life. Like I said, showers are super limited. So this is an astronaut washing her hair. You can basically get the water to stick to your hair and then kind of wring it all out and get a towel. And the water will just float around in little globs and you just have to pick them up. Here's some lighting at night. They try to keep it low light, like I mentioned before, to signify that it is time to sleep. And here are some astronauts playing with the Spheres spacecraft. They're little tiny guys that are meant to demonstrate things like formation flight and robotic helper spacecraft. So the astronauts are working, they do have a job, and so they are often doing experiments all day, either with biology or in this case, like engineering and test running different systems. So there is a very busy schedule. Really quickly to go over payload accommodations, things you have to think about. Will it survive launch? Will it survive re-entry? Do you have to bring it back? Is it built for microgravity? Do you want to land it in the water or on ground? Those are 2 different options. Does it plug into the ISS? You got to work with all the people who design the ISS to make sure that you can charge it or you can plug it in or it has a place to fit on the shelf somewhere. You got to make sure that that is obviously in the consideration. And then experiment results. Are you okay with contamination? Because if it lands in the desert somewhere, it might get some dusty air on it. Is it living? Does it have? Do you have to pick it up really fast once it lands? Does it need a freezer? Again, it's time sensitive. So all of these have to go into your payload accommodations. And when people are designing experiments for the ISS, they have to think about all of this and more. So that was a whirlwind, but I want to give some time for questions now and some discussion. And hopefully you got something useful or funny or some cool fun fact out of that. But yeah, I'll open it up now.
Okay, so go ahead and type your questions in the chat if you have them, or just unmute and speak up as long as no one else is speaking. And if you don't want to send your question to everyone, you can send it to host and we can read it out loud.
That's a good question. Can I just read them out?
Yeah, go ahead, of course.
Yeah. So have they changed the crew during the pandemic? How long they stay in space? Yeah, so that's a good question. There was a crew up there when the pandemic started, and they were up there for a few more months into the pandemic, and they left a world that was perfectly fine, and they came back into the middle of the summer of 2020. So obviously that was a big change. They have changed the crew a couple times, I think, since then. They haven't really, so NASA, the way they launch, well, NASA and Roscosmos and JAXA and all the space agencies, when they launch people, they already quarantine them for a few weeks. So there's a huge medical situation that they go through already. And so these astronauts, if they get the common cold, it's a big deal. And so there's already a lot of procedures in place to prevent someone from bringing COVID up to the space station. But your immune system does falter a little bit in space just from not being exposed to other people. So astronauts do have to be careful when they come back to slowly reintroduce people and not get sick. Have you been to space? I have not been to space. I would love to go to space. I have neither the qualifications yet or the money to go to space, but maybe someday. Is there an acclimatization program for astronauts after they come back to Earth? Yeah, they have a few weeks of stuff that they have to do, including, like I said, being kind of slowly brought back to gravity. They actually have to do an obstacle course. We try to measure their dexterity, and so we run them through an obstacle course, and it's hilariously bad. They'll just they can't do the straight line walking test that drunk drivers have to do and stuff like that. So we have to see what they're doing. They'll test them a week later to make sure they're returning to gravity correctly, rehydrating, make sure that they have all the nutrients they need and stuff like that, which they should have in space, but just in case they didn't, stuff like that. I don't know the details of what else they do though, but it's a week or two of reacclimatization. How does space debris so small cause damage to the spacecraft? Yeah, so the space station is traveling at 17,000 miles an hour. And if something, that's just what speed you need to be at to be in orbit, because energy is basically altitude in space. You need to get up there and get into orbit, and you're just falling around the Earth really fast. And if you're going that fast one way and something else is going that fast the other way, if you drop a penny off of the Empire State Building, that could probably kill someone, right? So that's just kind of the size differential. It's when something really small is going really fast, it still has a lot of energy. And so it can just be like a bullet through the space station. Do you have Wi-Fi? I believe they have Wi-Fi in space, which is kind of funny to think about. And so they do get internet connection, and they run all their experiments on the Wi-Fi and the internal internet on board. I got a DM being, what can you do after a degree in bioastronautics from someone who's very interested in astrobiology? Yeah, so for bioastronautics, you can work on, like I said, in commercial space, you could be working on something like Crew Dragon that SpaceX has designed, working on designing the interior of the spacecraft to make it nicer, or just designing spacecraft in general. We always need people designing spacecraft. You can do actually a lot of medical stuff. You can usually, a lot of the training that some people do and the research they do ends up kind of overlapping with people who are being rehabilitated from injury, from different eye diseases. Like I said, if you study vision for bioastronautics, you can do a lot of overlap that way. But work for NASA is the big one. If you study astrobiology, though, which is also included in that question, that's different. That's more of you're searching for theoretical life on other planets. So you're looking at exoplanets, looking at theory and what different environments could support life. So a lot more on the research side.
So we might need to regulate questions to save time. So I guess we'll just pick randomly from chat. Yeah. How are the UV rays from the sun regulated? And do astronauts get sunlight at all in space?
Yeah, the sunlight's hard. The UV light rays are going to be, basically the space station is still low enough to be protected a little bit from the direct UV rays. They're not going to get sunburnt immediately, which might happen in direct sunlight. But our atmosphere protects us, and the magnetic field protects us, and it still protects the astronauts a little bit. And they get a little bit of sunlight if they're by the windows. There's the kind of that window cupola room that they can go to. But we actually have UV lights in the space station to keep them from getting any sort of deficiencies that way, because they don't get enough sunlight. It's kind of like in Nordic countries when it's winter all the time, they'll actually put UV lamps in different rooms because people need sunlight to process vitamin D to stay healthy in certain ways. So we do that up there as well.
Combined question, how do we deal with waste, human or otherwise?
Yeah, so there's two ways. We can reclaim parts of it. Like I mentioned, we filter out some of the water that we can save. Usually with like poop or feces, we can't really do much about it. So we try to reclaim some of the water, and then we basically dehydrate it, and then we package it up and we burn it up in the atmosphere. That's how we deal with that waste. And same for packaging from food and stuff like that, and food waste.
And there's a lot of questions about pregnancy and babies being born. So would a baby be born and be fine in space? Are pregnant women allowed to travel?
No pregnant woman has been to space. No one has been pregnant in space. I would bet that we would not put a pregnant woman in space yet because we don't know what's going to happen if they're born. I mean, pregnant people, like during pregnancy, you're strong enough to like give birth without gravity, right? We don't need gravity, but like, what does that mean for the development of the baby? Like, no one knows yet. So we just haven't done anything like that yet.
And then how do we simulate gravity in space specifically?
Yeah, so I mentioned bungees. With working out, we try to load the astronauts by pulling them down to make sure that they're working their like muscles and their bones have that like need to be dense. We could simulate gravity using a centrifuge. That's actually been being tested for long duration missions like to Mars, because spinning on a centrifuge would actually have the same effect as doing much exercise. It would help just keep that bone density up, keep those muscles up. So those are two ways that we simulate gravity.
All right, and then last question: how can burning take place in space without the presence of oxygen? And what do we use burning for, maybe?
Yeah, so obviously on board the space station we have oxygen, so things can burn. You can see a candle in space would be a little ball because it doesn't rise the same way. But if something's burning, like say in the atmosphere, it's burning up as it goes through the atmosphere. That is still oxygen there. If the sun is burning, the sun is actually burning a bunch of different fuels. So it burns like hydrogen and helium and all the stuff that it produces inside the reaction that's going on the sun. That's like a whole bunch of other chemistry, but it doesn't burn oxygen all the time.
Okay, and I think that's all the time we have for questions, as it's already 10 o'clock. But thank you so much for coming and explaining all of this. I think you answered a lot of questions I didn't even know I had, and same for everyone else, I'm sure. And everyone here, thank you so much for attending. We suggest you all apply what you learned here to improve your final project for your submission, or just, it's interesting to know for your entire life. So good luck on the challenge. And as always, we're here to answer questions on the Terris Challenge Discord or by email. Questions about like logistics can be answered by any of the challenge managers, and questions about your projects can be answered by the mentors. More information about that coming soon. So thank you to everyone. And if you have any last words, Annika, please, go ahead.
Awesome. Yeah, I just want to say thank you so much for having me. And I know this is a challenge, so if people want those documents I mentioned, let me know and I can provide them or send you the link for those or the slides if people want to reference those. But good luck on the challenge.
Really cool. Yeah.
Yeah. But yeah, thanks for having me. I had a blast.
Thank you. Okay. Thank you, everyone. You guys can leave if you want. But yeah, lots of thank you messages in the chat.
For the documents